Hey, what's up?
Hi, nothing much. I mean, I'm happy it's Friday and we're done with work and I'm off on Monday to have an extra day for studying. So I'm excited about that.
Nice. Awesome.
Yeah. Yes. How are you?
I'm good. It's been a long day, long week. But yeah, I'm good. Thank you.
Yeah. I've definitely been a little stressed just because of like applications, but
Hmm.
I mean, we're getting it done. I'm just trying to submit everything by the second week of June and it'll be fine.
Got it, got it. All right. What would you like to do today?
So I think you were saying that you wanted to do like an hour and a half so I could go over the content review or like I wasn't quite sure what you were saying.
Hmm. Uh,
Um,
yeah, I don't remember, but
well, because I mean there's
hmm
parts of the content that I'm still not necessarily
hmm
fully grasping.
Okay.
I did the Jack Westin content diagnostic for Biochem and I finished the Chem Phys one. I realized like Chem Phys I'm definitely like lacking in a little bit more than
Okay.
Biochem. But I did like I don't know if you've seen the Milesdown review sheets.
Um, Not the review sheets, but um, yeah, no, I haven't seen them. I'm guessing it's like similar to what their Anki.
Yeah, they just have everything like broken down on here. Let me see if I can like there's like a
Oh,
biology section.
yeah, I see. Yeah. I see.
Yeah.
Um, yep.
So I was watching this one video on the biology section, so I got through that, and then like I was just watching more videos to try and like
hmm
really have everything memorized for like the organ systems because I think that's what I don't necessarily know for biology. Like I was kind of surprised, like I know way more biochem than I know biology. So
Okay.
yeah,
That's good because there's more like biochem is like the subject that's the most on the MCAT, like in both CP and BP. Uh,
oh,
and also like, yeah, no, knowing like the biochem and molecular stuff is definitely paramount. But yeah, we can go over any of the stuff. So this sheet, I have in
oh
the shared drive, and I also have in the shared drive, um, a similar type of sheet from Jack Westin that's also good. It's very similar, but yeah, they're pretty much uh, yeah. Okay, so yeah, let's go over some stuff.
yeah, I definitely feel like molecular bio though is not my strong suit. Because I was doing because I thought I had it down, so I was like, let me do some practice questions on UWorld, like with all the different like organ systems. And I feel like the questions that I was getting wrong were all molecular biology questions.
Hmm.
So should we go over like the UWorld questions? Would that be helpful or?
Yeah, so trying to think about what I said last time. So my I'm trying to think. I think it was something like, well, no, I was trying to think like if it was like, okay, part going over content from the content diagnostic and part going over like how to review passages, but we did go over passages together before, so um yeah. I don't remember. I'm sorry. But
No, you're fine. I mean, you were just because I was asking if I should take another practice test, and you were like, I should really make sure that I should get the content down before taking another practice test. And
okay. Got it. Got it. Yes. So okay, so you're mentioning like some bio content, but you mentioned also like the content oh, I think I remember now. So when we met last time, you did like the BB, I think,
Mhm.
content diagnostic, but you hadn't done the physics chem one yet.
No.
Were you able to do that? since last time?
Yeah, I did that one throughout the week, and yeah, that one was not as good as the
Okay, okay. Yeah,
yeah.
so I think we should start with that because I feel like organ systems and stuff like you could like kind of like learn like by reading and stuff, but like the Chem Phys stuff is super conceptual and can tie everything like kind of together. So yeah, I think let's do that.
Okay, all right. So I'll share my screen so you can see my
Hmm.
where I'm at in campus because it's not the best.
Hmm.
That's one share. I feel like with physics, the issue was that I don't necessarily know the equations.
So okay, so in your Anki, like miles down, like you have the miles down Anki or something, Jack or Jack.
I have like this Anki that has like all of the decks combined, which I feel like might not necessarily be too helpful. I feel like I'm probably just gonna scratch that and just get the miles down Anki because I think that's what people said is the most useful.
Yeah, so particularly, yeah, like because I'm like not aware of I'm not familiar with like a lot of the Anki decks, but I know for Miles Down, like there's a deck in the Miles Down like overall deck that's called Essential Equations, and it's relatively short, maybe like 60 cards, but um that I would prioritize just because it's an easy fix, right? If you don't know the equate like if you get questions wrong because you don't know the equation, that's an easy fix. And yeah, you definitely want to make sure you know those. But yeah, let's go over some of this conceptual stuff. Like I think like Chem Phys is very um high yield, even if it doesn't seem high yield, just because that's like the foundation for everything else. Like, like if you just take like an organ system and you just like go deep into it, you get to like the cellular level, you go deeper into that, you get to the molecular level, you go deeper into that, you get to the atomic level, and so yeah, let's yeah, let's make sure we get this stuff down. Um, yeah, okay.
Yeah, I feel like I don't know any of the periodic trends. I thought I knew them, but I
So so there's a reason that you chose this because you know that the trend for atomic radius, right, is like to the left and down, right?
hmm
But for so like the MCAT is like they're not going to just ask you something like as straightforward as that. So okay, so we can agree that like okay, open up the periodic table. So from here to here are most of the periodic trends, right? So
yeah.
there's electronegativity, electron affinity, ionization energy. They're all pretty related. Um, electronegativity is a big one because it's a measure of how strongly the element wants or takes electrons, right? Um, ionization energy is the energy to like remove an electron or like, add an electron. Electron affinity is kind of like electronegativity. They don't really specify that. Or right, like they don't really distinguish that as much. But yes, this up and to the right, that's where those periodic trends are, right? And atomic radius is the only one that's just in the opposite direction, right? So, you chose sodium because out of the choices, that does indeed have the largest atomic radius. So it's not that, you don't know the trends. It's just that the MCAT knows that you know that that's the largest atomic radius, but what they're asking for is the ionic radius. So what could be the difference there?
Like the ability to lose, like, um, or donate, like electrons or
So what's an ion?
ions, like a single charge.
So so it just refers to any charged like atom. So like because a regular atom um has it's neutral, right? Right?
Yeah.
Um, but an ion is charged, and and elements, atoms can take on a charge by either gaining an electron or losing an electron, right?
Hmm.
So sodium, the atom that I drew, uh, would become what type of ion?
Positive.
And what does that mean? Like what happened to it to get that?
It lost a, it lost an electron.
Hmm. Good. So now let's think about like, okay, let's see, like an atom has a nucleus with protons and an electrons will be like orbiting it, right?
Mhm.
So the they're also attracted to each other. So the nucleus, so what gives an atom its size is the nucleus pulling the electrons close to itself, as close as it can. Okay? So now, like, let's imagine that you are this proton and you're pulling this electron with all of your might, and this is the most you can pull it. It's this length, right? So now let's say that we go from one electron that you're pulling to two, and it's still just you as the proton. Now, do you think this would mean that you can pull the electrons closer, or would they be further?
I think they would be further.
Okay. Tell me why.
Um, because now instead of like having to account for one, you have to kind of like pull two, and it's like you only have there's only one of you.
Exactly. Good. So that would be if something was a negatively charged like ion, right?
Yeah.
Which we call an anion, right? Now, let's say that we started off with two electrons, but then we lost one. Now, what do you think?
Then it would be neutral.
Uh, like think about like the like the so like let's say these two electrons are like what it is naturally. Um, and if you lost one, when I say naturally, I mean like these two electrons gives you a neutral molecule.
Oh, I see what you're saying.
Yeah.
So if you lost one, then it would be positive.
Hmm. And tell me about can you like your ability to pull the electron or
Yeah, your ability to pull the electron would be greater now that you have less.
Yes, right? So that the ion now becomes smaller, right? Because you can pull it tighter.
Hmm.
So, and a positively charged ion is called a cation. And in between is your atom. Okay? So if we were just talking about an atomic radius, you're absolutely correct that sodium will have the highest atomic radius, but the MCAT is like not going to be that straightforward. They're always going to it's never going to be like that straightforward. They're always going to say something else about it. And so this question's really asking us about ionic radius. And when it comes to ionic radius, which would be the cation or the anion, the anion will always be larger than the actual atom, the actual atomic radius, and the cation will always be smaller than the regular atom.
Yeah, that makes sense.
Hmm. So like that's kind of what I mean. Like you can learn like physio, like you can learn like the kidney and nephron and stuff. Like, but like this, it's like it's less adding things to your knowledge and more kind of like being able to see things clearly.
Yeah,
So
that
yeah.
makes sense. So, okay, so that's because it was asking about the ionic radius, not the atomic radius.
Yep.
Gotcha.
Yep.
Yeah. A little. Okay, cool.
Mm-hmm.
That one. So it would be nitrogen 3 minus because it has the most amount of electrons.
Yep.
This is.
And then this one is just a knowledge thing, so just like add it to your either your notes or your Anki or whatever.
Mhm.
But this is just going to be a knowledge thing. But it also like would make sense because uh give me an example of some type of like hydroxide.
NaOH.
Yep. And Na is in the first in group 1A, right?
Yeah.
Yeah. And also this is it also makes like some hydrogen gas. So like I don't know if you've ever like you could even like see a video of like someone if they dropped pure nitrogen dropped pure sodium in water, it like explodes. But yep.
Yeah. Okay, I think I just thought that because
Hmm.
like oh the non-metals, I figured that chlorine was a non-metal, but maybe it's not. Like NaCl. But I guess you know what it is? It is soluble.
Yeah, so uh yes, yes. So this would be more accurate if it was group 2A. The group, yeah, because like these ones, I mean, like some of them, I mean, there's no like really clear kind of like other than like knowing like the solubility rules, but like magnesium, like that's very like soluble. But like barium is a lot less soluble. So yeah, so group 2 metals can be insoluble. So. Mhm.
Yeah.
All right. So, um, so now, yeah, this time, um, is also kind of like that other, yeah. So tell me what would have the highest just regular ionization energy?
Mm,
Oh, I forgot what the choices even were. And like, okay, let me write them on the side. Lithium, beryllium, sodium, magnesium. Okay.
okay. So it's asking highest ionization energy. Probably hydrogen.
So remember those periodic trends, right? Like going this way. So that's like pretty much all of the trends except for atomic radius. So that means ionization energy, electron affinity, and electronegativity. Okay.
Gotcha. Okay, so then I would probably say beryllium.
Okay. So let's see. Lithium, beryllium's more, that would have a higher ionization energy because it's to the right of it, and it would have more than Na because it's both to the right of it and above it, and it'll be more than the magnesium because beryllium's above it. Now, good, 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 good. Now, this is the MCAT, so they're not just going to ask you about the ionization energy, because they're asking about the second ionization energy now.
Oh, greatest second oh my gosh.
Yep. Now, now we have to like think, right? And like that's what you do on the MCAT. So the okay, so if we think about ionization energy is the energy it takes to like turn something into an ion, which would mean either like something gaining an electron or losing an electron, right? So something like, let's say, okay, so like I'll give like an example of a metal and a non-metal. So like for instance, fluorine, right? In order and like everything wants to fill its octet. So like fluorine um has 7 valence electrons. It just needs one more. So um so this can be ionized by gaining an electron, and then it'll have the same electron configuration as neon, which is going to make it very stable. So that's fluorine F minus, fluorine with, with an additional electron. Um, Now, when it comes to, let's say, magnesium here, so any given atom or element, um, when it gets ionized, it will want to have the same electron, uh, like number of electrons as one of these noble gases. So you can think like this, like, okay, magnesium can either gain one, two, three, four, five, 6 electrons to be like super stable, or it could lose one, two, right?
Yeah.
So which do you think would be easier?
I feel like it losing 2 electrons would be easier.
Yep. And that's why, it's Mg2 plus, right?
Yeah.
Okay. So now if we lose the first electrons, like the first ionization energy will be the energy it takes to remove one electron, like in the case of like a metal, because if it's like a non-metal, like it's going to be closer to gaining an electron. But magnesium, all right, will lose an electron and will take on the same electron like number as uh sodium, right? But would it be like satisfied there?
No.
No, right? So it's gonna get ionized again to have the same configuration as neon. So now if the ionization energy is the amount of energy it takes to ionize something, like in this case, to remove electrons, we can see that the first ionization energy would make this sodium, but it wants to lose 2 electrons. So when it gets ionized a second time to be this, that's where it wants to go. So it wants to have 2 ionizations. So it's not going to have a high second ionization energy because it wants to be ionized that second time.
Right.
But now if you imagine like a third ionization energy, that would be taking it from when it's having the same electron configuration as neon to fluorine. And does it want to do that?
No.
So this is going to have a really, really high third ionization energy because it doesn't want to do that. All right. Um, but it'll have a low second ionization energy because it wants to be ionized twice, right?
Hmm.
So now let's compare that to like sodium, right? So sodium, when it loses its first electron, will take on this configuration, right?
Yes.
And if it loses a second one, it'll take on that configuration. But is that something it wants to do?
Mm-mm. No.
So sodium's first ionization energy will be low, but its second ionization energy will be really high because it doesn't want to lose that second electron. Okay. So, yep.
I see what you're saying.
Yeah. And you see how it's like they want you to think just ionization energy, but there's like, it's not just asking for that, it's asking for the second. So, yeah, and so it'll be lithium. So yeah, if you open that up again. So this lithium, right, it'll have a low first ionization energy in which it'll lose an electron and be having the same electron configuration as helium. And then it would lose if it loses another, it would go all the way to having the same configuration as hydrogen, which it does not want to do. And so it'll have a very high second ionization energy.
Okay, that makes a lot of sense because that's like a long way to travel. It's basically back to where it came from. LOL.
Hmm. Yep. And you see how like sodium follows a similar pattern, right? But we also know that from the periodic trend that up and to the right is going to be a higher ionization energy, like first ionization energy. But if you have a higher first ionization energy, then your second one can go higher too. So that's why lithium will be the answer because it's above the sodium.
Gotcha. And yeah, I see.
So, so it's like, yeah. So it's like they ask you about something that you recognize from Gen Chem with periodic trends, but then they ask you something like a little bit, like they tweak it a bit to ask you a question.
Yeah.
Mhm.
This one.
Well, that's good. You got all these math ones right. Like that's really good, actually. Most of the time, people have issues with those.
Good.
Um, yeah, that's impressive.
Okay, good. LOL. I definitely
Hmm.
spent some time on these. Like, I feel like I want to get better because I feel like I spent a good amount of time practicing like how to do the math ones, but
Hmm.
yeah, it'll come with time. I mean, I'm like, is there one that was stressing me? I feel like probably this one, but I mean, I was able to get it, so maybe I just need to keep practicing.
Yeah. So, um, yeah. So I was gonna say like we can maybe look into like how you would do it, but you've gotten all these right, so I feel like you
Yeah,
already do
I'm,
that.
I'm probably fine.
Mhm.
Um, which of the following correctly pairs an ion with its molecular formula? I think this is just naming. It's like I just didn't know.
Yeah, yeah. So, yeah, so this would be like, something to like Anki. Um, and yeah, like particularly like, like this and this are important. Like this is called bicarbonate. Um, and then this is uh wrong, meaning a phosphate would have four oxygens. But yeah, it's pretty much just knowing the polyatomic ions.
Oh, yeah. I feel like I have trouble with solubility questions.
Got it.
You have
Yeah.
to put the ice table, right?
Uh, Fortunately for the MCAT, like rarely, like meaning like, because you know how if you do like the ice table, um, and it's like some amount minus X, and like if X is really, really small, it's negligible. If it's not, it's not negligible. But I've never really seen an MCAT question where that X value is like not negligible. So yeah, don't have to worry about that, thankfully. Um, but everything with a capital K is derived from something called the law of mass action, which is essentially product concentration over reactant concentration. Okay. Meaning like um I don't know, like let's say we have AX2 turns into A plus and 2X minus. Your K is going to be concentration of, so products first, so A plus, and the other product is X minus. And if we have a coefficient like this 2, we put it up, we turn it into an exponent like this, and then it's going to be over the concentration of the reactant like this. Now, um, For okay, so for these, since these are all concentration terms, um, it wouldn't make sense to include pure substances. Like,
Like water.
yeah, right? So like people just usually say like don't include solids or liquids, which is true. But I want you to see like why it's true because what would, the concentration of pure water be like? It would just be like one or like 100%, right?
Hmm.
So we don't include that. So in the case of most stuff with K, like so like Ka, Kb, KOH, K um affinity, KB, KW, KSP, KEQ, all of those. They all come together in this law of mass action. Um, and particularly for solubility, since you're starting with a solid, you won't include that in your setup. So KSPs typically won't have a denominator.
That makes sense.
And and then the other thing is that when you do the math, um like I'll use green here. So like if we say this is X, this inside here, I mean, I guess I used X for for this, but I'm trying to say like, when you turn it into X, like,
Hmm.
actual molar solubility, like this is going to be 2x in parentheses squared, right? And what would this turn into then?
Um, 4 times x squared.
Good. And then times this x, right,
Right.
would then give you ultimately,
4 times x to the third.
yeah, good. So there's three like possibilities here. So, if it broke apart into two, like if this two wasn't here, then this would be x, this would be x, and multiplying the two would give you x squared. So that's that scenario. If you have something like with two here, you can get this scenario. And then lastly, it's like if we had something like x times in parentheses 3x cubed,
Hmm.
this would turn it into what do you think this would turn into?
Like so in terms of like the A and the X.
Oh no, just like here we did like this.
Oh, yeah, sorry, my bad. It'll be 3x. No. It was 3 to the third is 27. I think it would be 27 times x to the fourth.
Yep. So so basically like these are the three possibilities that you'll have.
Hmm.
So and yeah, there won't be any others. All right, good. So now so they're telling us that yes, this whatever breaks apart. Um and this like you should be able to like kind of see like what this would break apart into, right?
Yeah.
Like barium 2 plus and sulfate 2 minus. And these will have like an equivalent concentrations, right?
Yeah.
So we could say this is X and this is X. So it'll be the X squared example, right? And then you just take the KSP value, which is 1.1 times 10 to the negative 10, and you set it equal to the X squared.
Right. And then you just take the square root.
Yes. Now, how can we do that? Because it's not like, like it's not like square root of like 36 or something, right? Like, so,
Um, I'm like, isn't the square root of a exponent like you just divide that by two, right?
so kind of something like that. So we could think about it like, like this, like, okay, so let's say, okay, X squared is what we start with, and we want X, just X.
Mhm.
And just X has an exponent of what?
One.
1, right? Now, do you remember like the exponent rules? Um, like,
Yeah.
yeah, okay. So we want this exponent 2 to turn into an exponent 1. So any ideas about how we can do that?
You just divide by x.
So we could take this to the power of something, let's say y, and if you take an exponent to the power of another exponent, what do you do with the exponents?
You add them.
So let's
No.
so let's do this. So let's say we have x to the power of a times x to the power of b. This is when you would add them. And let's say we had x to the power of a divided by x to the power of b. What do you think this would be?
It's when you subtract like a minus b.
Yep. Now x to the power of a to the power of b.
Okay, so you multiply them, I guess.
Multiply them, right? A, b. So here, right, if we're taking x squared to the power of y, we want to think 2 to the power of what, or 2 times what will give you 1.
Oh, like one half, like 0.5.
Yep. So 1/2 is a better way of thinking about it, right? Because like in general, I always say fractions are better, but especially in this case, because look, if you did 2 times 0.5 that's like whatever. It's not that nice. But if you did, if we're trying to get one, that means we're trying to get rid of the two. So how do you do that? You multiply it by something that has a denominator so that the twos cancel. Okay. So um, if we had x cubed, how would we take the cube root?
Um, you would multiply it by 1/3. Well, I guess you would put it to the power of 1/3.
Yep,
Like X, yeah.
absolutely. All right, good, good, good. So okay, let me just clear this up. So now we have 1.1 times 10 to the negative 10 is equal to x squared, and we need to find what is it? The x.
Yes.
So what do we do?
So to get X to 1, you would do X squared times 1/2, and then you would do that to the other side as well. So you would put the 1.1 times 10 to the negative 10 in parentheses, and then put that to the 1/2 as well.
Good. Now, 1.1, I mean, whatever, that's like 1, right? So let's just leave it at that. And then it'll be to the power of.
-5.
Good. And there you go.
Okay, that's way easier than trying to find the square root. I feel like I like once upon a time remembered this trick, but it's
It-
coming back. It's coming back. This okay, cool.
they never really tell you this stuff when they teach it. Uh, like so that's why, because if they taught it to you, like, all right, everyone knows how to do like a square root, but like why did, uh what this is 1/4 of people chose B, 1/5 of people chose C, right?
Hmm.
And these are smart people, so it's like people know how to do square roots, but this is like being able to see that type of math that when we learned it in like middle school or high school, like there was no real way to actually find the square root of something. It's just that they gave you perfect squares,
Yeah.
right? So, um, it, interestingly enough, I remember like I one day like many years ago, I was like on a quest to figure out how to find the square root of numbers that are not perfect squares, and like I was in Subway, and it was like the delays, and I just spent the entire time trying like to figure it out, and I figured it out, and it was pretty cool. But anyway,
Cool.
because oh well, the reason that I'm saying that is because, so for instance, right, let's say that you had, or how about this? What if we need to find the cube root of this?
Cube root with X still being squared.
Sorry, it'll be like the 4x cubed thing, but and you would have to divide the 4, but let's not worry about that. Let's just think, okay, if we had to take the cube root of this, what what would we do?
Yeah, so then I think it would be the same where you would do the 1.1 times 10 to the negative 10 in parentheses to the 1/3.
All right, now continue.
So I guess like it'll be 1 to the 1/3, which will just be 1, and then it will just be 10/3.
Okay. Now, uh that's gonna give us some like non-whole number, right?
Hmm.
So maybe we can like express this term a little differently. So, so what I mean is, let's choose an exponent that's divisible by 3.
Oh, so you could do like 30.
When you say 30,
Yeah.
what do you mean?
Well, would you multiply I'm like, well, how do you switch the exponent? I was just assuming like it would be that 30 would be easy to switch to. Maybe 15.
Well, so you know, uh we can't like change like that number,
Mhm.
but we can change how it's expressed. So what I mean is, um, so and now, so what I'm going to show you like is something that every time I do it, I say this out loud just because like like it's the MCAT, like you're not going to be it could be cool to be able to do fast math in your head and stuff, but I always stress relatively slow systematic approach to eliminate mistakes. So I want this to be divisible by 3. So I could choose, I'm going to choose to turn it into like -9, right? But you can have it turn into like -12. But the thing is that we can't just like change the number. You have to make it still equal to this. So what I'm going to do is, since I'm making this exponent number um larger, it's 9, but it's -9, so it's larger, right? Um, whatever I do here, like I'm gonna have to move the decimal point here.
Mhm.
Whatever I do here, I do the opposite here on the right. So what I mean is, so on the right side, if I want to add to make it -9, on the left side, I would have to subtract. And by subtract, I mean move the decimal point to the left. So I'm going to say left subtract, so 0.11, and then right add, so it's to the power of -9.
Right.
And this is still the same answer, same number as this, right?
Yeah.
So yeah, that's a way that we can then have, we can do a cubed root because the 9 is, divisible by 3.
Gotcha.
Yep. So let's see. If you had 6 times 10 to the 12, um, to the 11th power, and you wanted to turn it into the 12th power, um, how would we be able to do this?
Then it would be like but it's not negative. Oh, wait, you're trying to turn it into 12, so you're adding
Hmm.
a 0. Making it bigger. Oh yeah, so then it would still be I think zero point 0.6 times 10 to the 12.
So it's like, okay, on the right side, if I want it to be 12, I'm adding on the right side. And on the left side, I would subtract, so I'm going to move the decimal point to make it a smaller number. So, yep, exactly that. Makes sense?
Yes.
Good.
Um, yeah, this is probably
Oh, yeah,
just
this is like that other question. Yeah, this is just something to know. So you should be able to see that or know that this is carbonic acid. And and also when it comes to like just any of these things, like since you want to think interdisciplinarily, like it's not just you don't want to see this as like a disjointed kind of they're just asking you what bicarbonate is and it's like that's it. You want to think, okay, bicarbonate is the buffer in our blood that keeps our blood from getting too acidic. Um, right?
yes.
And it's related to like carbonic anhydrase. Um, even like a carbonated beverage has like carbonic acid because that's a reaction that happens. Um, so oh, and then this is also an example of a polyprotic acid. Um, so what that means is, so carbonic acid can donate a proton to turn into bicarbonate ion. So this is the acid, this is the conjugate base, right?
Mhm.
Now, since it's a diprotic acid, this conjugate base could also act as an acid because it could donate another proton and then just be the carbonate ion. Okay. And like this is why this is a buffer, right? Because it's like, okay, if your blood gets too acidic, which happens from carbon dioxide, like this amount goes up,
Mhm.
then the bicarbonate, um, which is both a conjugate base of the first reaction, but an acid in the second reaction, can act as the conjugate base, right? And take some of these protons to make this. Um, or let's say that um your blood is more basic, right? And so therefore this number goes down, then this can go in this direction to produce more H plus, right? So
Yeah.
this is a buffer. Yep.
Do this one.
Oh yeah.
Um, okay. The Bronsted Lowry acid, um, they they donate protons.
Yes. So um before that, I want you to be able to like draw what these look like
Okay.
from like yeah, their structures just to yeah, just to make sure.
That's a CH4 and then whatever.
Yep, just methane, good.
Okay. I'm trying to figure out how to draw the third one. I'm gonna get it though. I'm gonna get it.
Oh yeah, you can tell me what the second one is.
Oh, okay. Yeah, I got the second one. Here, I'll show you. It's this one.
Yep. So that what was so like what type of molecule is that?
Alcohol.
Hmm.
Um,
Specifically like methanol, right?
yeah, methane.
You could try D first before C.
Oh, okay. Yeah, that'll probably be easier. Oh, this one's D,
And what type of molecule is that?
the ketone. I feel, oh, okay. This is a carboxylic acid.
Mm-hmm.
Yeah, that's why
Yep.
she looks funny.
So that's why there's like the two oxygens, right?
Yeah, and six hydrogens.
Mm-hmm. Now, like, so you're still drawing it, which is good. Um, because would it be safe to say that, okay, it has two oxygens, so it will be an carboxylic acid?
No, because it could be an ester.
Exactly. Yeah, perfect. Great job.
Okay, cool, cool. So it says, oh, Bronsted Lowry acid. I
Mhm.
guess, yeah, the carboxylic acid makes more sense because it has that extra OH.
Yep, because it's literally the an acid, right?
Yeah.
And so and also like the reason is that when it loses its proton, this is resonance stabilized.
Yeah,
So it's going to be more stable after it gives away a proton.
gotcha. Okay, we know her.
Okay. This one, there's like I'll show you the like logical way to do it. And then like the actual like proper way to do it. Um, well, okay, I'll start with the proper way. So, well, before that, okay, how would you do this? Or like yeah, what's your approach here?
I was honestly confused because of the 2.30. Because I feel like they normally give us like whole numbers, so it's like easier. So I knew it would be 12 and actually I didn't know.
So, what uh so tell me about pH.
pH is the concentration of the hydrogen ions in solution.
So it's just the concentration? So if something has a pH of 4, it has just 4 like protons or something?
No, I mean not just the concentration. It's like its ability to, I guess like the amount of hydrogen that's in solution. I guess that's still concentration. Um,
So, um, so I remember in first grade, people were telling me that the number after 100 is 101. And I was like, that doesn't make sense. Number after 100 should be 200. And that's because I was thinking, I mean, I didn't know what it was, but logarithmically, um, for instance, right? Like if you had something like this, where you have a lot of change in terms of the y direction here, in a tight range x direction, right? Uh, it's hard to really, you know, do anything with this. Um, but if we turned it into and by the way, this is like an exponential thing, right? And logarithms are like the inverse of exponents. So if I did the log of this, it would turn it into like a linear line. So uh that's why logarithms like are used so often in things like in pH because like um if your pH goes up by 1, you are really adding 10 times the amount of protons. Or I guess removing, right? Um, so we so your pH technically the equation is negative log of the H plus concentration.
Yeah.
Okay. Now, um, the inverse of a log, or like how would you like get rid of a log term, let's say?
Take it to the power of 10.
Good. So if we want to go from pH to H plus concentration to get rid of the log, we would then do 10 to the power of pH. Oh, and it's a negative log, so to the power of negative pH would equal H plus concentration, right?
Hmm.
So this could be a way for you to go from pH to hydronium concentration.
Okay.
And now going from hydronium concentration to pH, you would have to do the negative log, but like I'll just show you like the shortcut for that. So let's say that we had like 3 times 10 to the negative um 11 power, like molar, as our H plus concentration. And I want to find the pH of it. What I'm going to do is, well, the negative log of it, which is really just you take the exponent and you change its sign to be 11, and then you subtract it by the log of this number in the front, like that. Okay? Now, I used to have like my students know the values like log of 2, log of 3, log of 5, log of 7. Um, because well, with those, you can figure out the logs of everything else. And also because they happen to equal certain cosine and sine values, so you can kind of like associate those. But um, over time, like I realized like a lot of the questions didn't really specify like they weren't really asking anything like that like detailed. So what we can do for log terms is so like log of what's log of 1?
Okay.
So for logs, like if you have a base 10 and let's say this is A and then this is X, remember
Oh, yeah. So then be 10 to the 1, which would just be 10. Wait, no, no, no.
that we want to think 10 to what power equals 1.
Oh, 10 to the 0.
And log of 10.
Then this is 10 to the 1.
So now anything, the log of any number between 1 and 10, you could just approximate as zero point 0.5. And this will be enough for like for any log questions. Um, so we could say this log of 3 is zero point 0.5, so we could do 11 minus zero point 0.5 to get 10 point wait, what am I doing here? Log of 11 minus 3. Oh yeah, yeah, this will be just like 10.5, right?
Hmm.
Um now technically log of 3 is point well, whatever, we don't have to worry about that. But yes, so that's what we can do. So if we um look at these values for something that we want to equal like 2.3, um, well, we could just kind of do each of these. So like for instance, this, uh, let's do that to it. So what do we do here?
Um, so this will be 12 minus log of 2.
Okay. And
So then log of 2 would be, I guess, like 0.5 maybe. And 12 minus 0.5 would be 11.5.
good. Good, good, good. So that's not matching the 2.3, right?
No.
So let's try this one.
So we do it again, which is 3 minus log of 5, which is 0.5. Yeah, log of 5 is 0.5. And yeah, 2.5.
Mm-hmm. And
Is
that, yep,
close.
that's the closest to this, right?
Yeah.
So yeah, so that's the proper way to do it,
Okay.
and it makes sense.
Yes.
All right, and now another way that we could have done this was it's a strong acid, right?
Yes.
And they're saying hydronium and hydroxide respectively. So the first number is hydronium, H plus, second is hydroxide. So if it's a strong acid, it should have a lot more hydronium than hydroxide, right?
Yeah.
A, B, and C all have much less hydronium, right? To the, like 10 to the power negative 12, and much higher hydroxide, right?
Hmm.
So the only choice that has a higher amount of H plus is D.
Yeah. I must have missed that one.
Well, probably a lot, yeah, like, 41%. Yeah, yeah. But yeah, so this is like another kind of good example of like um if you just go straight to like a formula or something like that, um you want to be able to see it conceptually first. So I showed you how to do it with like the formula and like the math. But then also conceptually there's it's the only choice that has a higher amount of, hydronium.
Look at this again. I don't know. I should know. Actually, never mind.
Oh yeah, so well this isn't any type of atomic trend, periodic trend or anything like that. Um but what is like what does a reducing agent do?
It adds electrons.
Tell me more, like to what? Like to something else?
Yeah, to something else.
Okay. So it itself gets oxidized, right?
Yeah, because you're taking electrons from it.
So we're really asking, okay, which of these halogens is most likely, right, to give away its electrons.
Yeah. So I thought it was fluorine because it was the most electronegative.
So what would electronegative be? Like the like
Has a good amount of electrons.
so electronegativity is how strongly something wants and takes electrons.
Oh, okay. Okay. All right.
So, yep.
That makes sense. Okay.
Yeah. That's why, like, and there's so many things that you can figure out from just that. Like oxygen is very electronegative, right?
Hmm.
So like all of the catabolic processes in our bodies that is like, when you break down molecules, that they're all oxidative. So that means that they are losing electrons. So if you're breaking down like, protein and carbohydrates and sugar and, fats and all that stuff, um, you're oxidizing them, which means you're taking their electrons. But like, why? And it's because you ultimately give those electrons to oxygen because oxygen is very electronegative. And like that's going to be that like also like, when they say like to memorize the polar amino acids and the non-polar amino acids, you should be able to tell from a molecule if it's polar because it'll have something that's very electronegative, right?
Yeah.
Like if you have a ketone, oxygen is super electronegative, so it pulls electron density from the carbonyl carbon towards the oxygen, producing a partial positive on the carbonyl carbon and a partial negative on the oxygen. So,
Okay. Yeah, I feel like maybe I just had this concept confused. Like I think I just had it backwards, maybe. Because I was thinking I would need like the biggest number, but I was wrong. Um,
so, so, um, let's see. So, first of all, just these numbers isn't enough for us to tell anything because they could be oxidation potentials or they could be reduction potentials, right?
okay, yeah, I thought they were reduction potentials.
Oh, they are.
Okay.
So, because in this question stem, they say reduction potentials, right? So
Yeah.
these happen to be, I'm saying like from the numbers alone, you can't tell, but they're telling us that they're reduction potentials. Now, the thing is, though, if you are a reducing agent, what do you do?
You give away electrons.
So you reduce other things, right? So, or if you give, so oxidation is when you lose electrons.
Yeah, like that the thing that's oxidizing loses electrons.
Uh-huh.
Okay.
So, oh wait. So, if you yourself are oxidized, you lose electrons
Hmm.
to give to other things. So you reduce other things, right? So a reducing agent is something that reduces other things, right? Which means it itself gets oxidized.
Yes.
So what you're thinking is right. This one is going to be uh the most reduced, right?
Hmm.
But since we're being asked which is the strongest reducing agent, we're really choosing whatever is the most likely to be oxidized, right? And so the smallest reduction potential will be the most likely to be oxidized.
Okay. So I mean, so this doesn't necessarily have anything to do with the delta G equation because I was thinking about no, okay.
Well, no, you're thinking about this.
Yeah.
And so yeah, it like if you are dealing with, some redox reaction, the cell potential would be the sum of the reduction potential and the oxidation potential. And so okay, let's pick like okay, this and this for our redox reaction, right? And since these are all reduction potentials, oops. So the one that, so for the gold, you have a reduction potential of 1.52, and then for the aluminum, you have a reduction potential of negative 1.66. So when we're dealing with reduction potentials, whichever one has the higher reduction potential is the one that gets reduced, right?
Okay, that makes sense. Yeah, because so then it would be um gold getting reduced.
Yes. But that also means whichever one has the smallest reduction potential must be therefore oxidized.
Yes.
And so that means so to go from reduction potential, so for instance, aluminum 3 plus 3 electrons gives you aluminum. This is a half reaction for reduction because reduction means gain of electrons. So on the left side, we are adding electrons, right? But now, if we're doing it with both of these, the aluminum will have to be oxidized, which means it's going to go in this direction. And what that means is, so like any given reduction potential is the same as the negative, or the negative of a reduction potential is the same as its oxidation potential. So now this turns into aluminum breaking down into aluminum 3 plus 3 electrons because this is oxidation. And its oxidation potential is going to be the negative of its reduction potential, which would mean positive 1.66, right? And so your total will just be 1.66, like meaning 1.52 for the reduction plus 1.66 for the oxidation to give you your cell potential, which is what that is.
Gotcha. Okay.
Yeah.
Yeah, I would probably just need to like keep working on like making sure I know like the difference between the agent and the like the oxidizer. Like I feel like all those terms are like a little trippy.
Hmm.
This I feel like I don't know. I think I just guessed, but aren't London dispersion forces similar to like hydrogen bonds in a way?
So, okay, so last when we talked about like the coordinate covalent bonds, right? We talked about like actual like covalent bonds and how they're like actually bonds and how intramolecular bonds are not like we don't draw them as like, lines, but like dashes and stuff. And so these are examples of intermolecular forces or intermolecular bonds.
Hmm.
So now there's, so if I had, whoops, a carbonyl here and an NH thing here. This can be a hydrogen bond, which happens between hydrogen and something either that's F, O, or N. And that's the strongest type of intramolecular bond. Okay. You can have also dipole-dipole interactions. So that could just be um, like an O, or something like this and something like, let's say, maybe something like this. Basically just like the something that's like partially positive with something that's like partially negative um, for your dipole-dipole interactions. Um, London dispersion forces are the ones that are always present no matter what. They're also known as van der Waals. And the benzenes are non-polar, right?
Yeah, I feel like I'm definitely bugging because I guess I just thought hydrogen bonding was just bonds between two hydrogens, but like no, that's not what it is. This
Correct, yeah. You're going to need these guys.
yeah.
And like, why do you need these guys? Because they have high electronegativities. And if they have high electronegativities, they can participate in interactions with things that have low electronegativity. Sorry. Um, well, this oxygen would have a high electronegativity, and this nitrogen would have high electronegativity. So that will be partial negative. This will be partial negative, but the proton will be, or the hydrogen will be partial positive.
Right. So
Uh, yep.
would that be a dipole then? Between the hydrogen and the oxygen?
Um, so this one in particular would be like a hydrogen bond. But it is still using dipoles, so maybe we could say hydrogen bonding can fall under the category of a dipole-dipole interaction. Uh,
Okay.
but uh but for these two benzenes, like the best answer would have been hydrophobic interactions because they're both hydrophobic. Um, but that's not a choice. And so when we look at these, like, okay, dipole means that there must be a polarity, right?
Hmm.
But these are non-polar, so it can't be that. Hydrogen bonding must require hydrogen and F, O, or N. We don't have any of those, so that's out. And yep, all that's left would be London dispersion.
Gotcha. That's okay.
Okay, so for this one, you probably just didn't multiply by two.
Yeah, I feel like that's
And yeah.
fine. I was thinking maybe we could get to some chemistry things just before we run out of time.
Oh yeah.
I mean, not chemistry, physics. I'm looking physics.
Hmm.
Um, okay, let me see. I wish I could just like click on the questions to figure out like
Yeah. You can go back to where you were, and I think like by question like 70 or something, it gets the physics stuff. Okay. Mhm.
I mean, I guess we could go over this. I'm like I just don't want to miss the magnetism part. LOL.
Okay.
It's fluids. No, it's probably back this way. I don't know where it would be, honestly, but
Sorry, what are you looking for?
um, I guess like those eight questions I got wrong in the I think it's like electrostatics and magnetism.
Okay.
Is this mo motion and waves?
Yeah, so just know that light is an electromagnetic wave, meaning that as a photon moves, it has like let's say this is the direction of the movement of the photon. Perpendicular to that will be an electric field, and then perpendicular to both will be the magnetic field.
Hmm.
So, um, but yeah, we can you can go forward. I'll see if I find stuff for that electrostatic and magnetism and stuff. Um,
Mm, yeah, maybe it's like in the
yeah,
50.
it'll probably be before like the one that I said, or like 70 or whatever. All right, torque. Okay, yep, you can keep going.
It's probably before that then, like maybe the 40s.
Mhm. Okay,
Oops.
so it'll probably be after this because it's still like chem. Okay, starting the physics now.
I'm not seeing it. Am I just going too quick? Oh, here's some stuff.
All right, yeah.
I guess we can start here.
Okay, so this is just by convention. Um, Electric field lines go from positive to negative. That's just by convention.
Okay. Yeah. Okay.
All right, now, yep. So this is a common type of question. So, okay, so the universal law of gravitation is this, right? And the electric or Coulomb's law, which describes the electrostatic interaction, is this, right? And you can see how they're taking on the same form. It's just that gravity is between masses and electrostatics is between charges. Okay. So they're saying here two charges, Q1 and Q2, are separated by a distance R. Force is the electrical force between the two charges. If the magnitudes of both charges, oh wait, yeah, of the charges are both doubled and the distance between them is quadrupled, what would be the electric force between them? Okay, so we're going to double Q1 to turn it into 2 times Q1. And we're also going to double Q2 to get 2 times Q2. And when you multiply these, what do you get?
Or um, and then in parentheses, it'll be Q1, Q2.
So this would produce a 4 times increase in the force, right? Now, we are also quadrupling the distance between them, right?
Yeah.
Which is what this R value represents.
Hmm.
Now, 4 times the R value, but we are supposed to square that R value, right?
Okay.
So this squared would be what?
16 R squared.
Good. So now we have a 4 numerator and a 16 denominator. So what do we do there?
Um, just divide it. It'll just be like 1/4.
Exactly.
Yeah. I feel like I did not know Coulomb's law. I thought I knew it, but I guess I really thought I knew it, but it's okay.
So we're gonna make sure that you Anki the
Essential equations by Milesdown.
Yeah.
Yeah. And then this is just the units.
Okay. So an amp and also like to be able to deconstruct units is important. So yes, for current we use amps, but you want to be able to deconstruct it. So what I mean by deconstruction is like a Newton, like deconstruct that for me.
Isn't that like kg? Wait, hold on. Uh, yeah, kg over.
So uh what um so Newton is a measure of
Force.
okay.
So
And,
yeah,
and force, what could that like any formula come to mind with like force equals something?
yeah, ma.
All right.
And I'm just like acceleration is
Yep.
meters over second squared.
Mhm.
Yeah, so kg times m over second squared. Okay, yeah. There we
Good.
go.
Okay. Yeah. Good. So you're able to do that. Good. 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 This is very important because it's like if you don't remember the formula, you can use the units to figure it out. If you don't remember the units, you could use the formula to figure it out. So in this case, like, you're starting off right with like kilograms, but then I just asked you like, okay, what is it a measure of? You said force, and you remembered the equation F equals ma, which is really sum of all the forces or net force equals ma. But yeah, you were able to tell me, figure it out based on that equation, right? So same thing with amp. It's going to be what's the unit for charge?
Uh, is that Coulomb?
Hmm. So coulombs per second. Charges per second. Because like a current is like, the movement of the electrons, right?
Yes.
So, and an electron has a charge, and it's almost like kind of like velocity of the electron that's moving.
Yes.
So, so yeah, an amp is coulombs per second, and um, oh, and then electric field. So, all right, so for the little g value, right? You know it has like 10 meters per second squared, right?
Mm-hmm.
Which is like the gravity, acceleration due to gravity in Earth's uniform magnetic field.
Yes.
And that comes from if we plugged in for mass one here, the mass of the Earth, and for the radius, we plugged in the radius of the Earth, and g is already a constant, this turns into that.
Okay.
Now, from F equals ma, or I guess mg, if you rearrange this, you can get g is equal to what?
F over m.
And that would be newtons per kilogram, right?
Yes.
So now this is exactly the same as this, right? But this is can describe the strength of the gravitational field on the surface of the Earth, meaning, so this is 10 Newton per kilogram, meaning that on the surface of the Earth, um, a mass will experience 10 newtons of force per kilogram. Okay. So now, and that's the gravitational field. Okay. Now, here, like just like this, if we had, like a parallel plate, like kind of thing with like stuff here, like two plates, right? With uniform electric field between them.
Hmm.
right? Uh, would have a known, distance between the two. So same thing. This turns into this, which is the electric field. And just like just like the gravitational field is the force you experience per kilogram of that mass and that's because gravity occurs with masses, right? What do you think it would be for the electric field here?
Okay, so if amps are
Oh yeah, don't worry about amps yet, just from here.
okay, I guess I'm just a little confused about the connection of the
Hmm.
force of gravity to the electric field.
Yeah. Um, so like if you have for the gravity term, like this thing that I circled, which is like would inc we would input in like known values, would give you your little g, which we can think of as, in addition to acceleration, we can think of it as the uh, strength of the gravitational field.
Hmm.
So that's why this can turn into mg, with m2 being the mass and little g being this entire thing. And so in a force field, something will experience a force which is in newtons per whatever uh
Kilogram?
yeah, like if it's so we know so gravity exists when you have masses, so that's why it'll be per mass, like newtons per mass or newtons per kilograms, right? And the electrostatic force is not between masses, but it's between
Mhm.
what's up?
It's between like two different charges.
Yep. So it could be just like this, except instead of the kilograms.
It would be coulombs?
Yep.
Oh, okay, that makes sense.
So the electric field we can think of as again, like the force that something will experience, that a charge will experience in that uniform electric field.
Okay, and then I guess you could put the coulombs equal to amp. Seconds times amps.
Yep, yep, yep. So let me clear this. So if an amp is coulombs per second, and we want to find this, right? Um, what would we do? I guess you also know, so like this would be what again?
Uh, Kilograms times mass over second squared.
So the M was something, what?
M is meters per second squared.
Mhm.
My bad.
You're good. And so that's newtons. So then we just divide this by coulombs.
Oh, okay, the whole thing. Okay. And then,
Or rather, since these are using amps, right? We would um have to do something in order for us to have like the coulombs on the bottom, right?
yeah,
So um we could maybe let's try we want the coulombs on the bottom. So I would want amps to be on the bottom, right?
yeah,
And divide, like, I guess I'll do it with so I can divide it by, so if I divide it by coulombs per second. Okay, so before I do this, like, the if you divide something, it's the same as multiplying it by its reciprocal, right?
hmm
Okay. that's, I think, a better way of doing this because, and it's funny because I say that there's no subtraction, there's only addition and addition by a of a negative. And I also say there's no division, there's multiplication by a reciprocal. Because that way I can just, it's simple. I could think of things like you just add them, you know?
Right.
I also say there's no division, there's simplification of a fraction, like 32 over 8. I'm not doing 32 or 8 kind of thing. I'm like, this goes into this 4 times, right? So okay, I'm gonna multiply this by, well, I'm gonna divide it by amps, which means dividing it by coulombs per second, which is the same as multiplying it by the reciprocal of amps, right?
Hmm.
Which would be, what's the reciprocal of coulombs per second?
Seconds over coulombs.
Good. So now I have my coulombs on the bottom as I want, but this and this cancel, and I end up with, well, I don't have my Newton anymore, right?
No.
So maybe I would need to do like kilogram times mass over seconds cubed and multiply that by the reciprocal of amps. So then this and this could turn into that. So this is our newtons and over the coulombs. Right?
Yeah, I guess I'm confused about the cubed, like the
Mm-hmm. Yeah, so like, here, I'll use green. So like if we look at these choices here, so we know that, well, okay, first of all, we know that, so this is kilograms times meters over seconds, right?
yeah.
And that would just be like mass times velocity, right?
Hmm.
It won't give us a force because it's a force would have to be mass times acceleration, right?
Oh wait, no, no, never mind. I got it. I'm sorry. I forgot. I didn't realize that's what you were doing up here. Like right here, you were the S's here.
Yeah, yeah. Because yeah, first I tried um doing like yeah, newtons times or newtons divided by amps and I lost, um like a second there and then you no longer have newtons. So I need to adjust it so that if I lose a seconds term, I can still at least have seconds squared. So
Yeah.
so if I did, so that's why, like, yeah, so like this one has just, oh, newtons over, or rather kilogram times meters per second. And that would give you, like, the seconds will cancel. This will just be kilograms times meters times coulombs, or rather divided by coulombs, right?
Yeah.
And then this one is the one I started off with here. And that won't work either because the seconds will cancel and you'll just have 1 seconds on the bottom, right? And then this one solves it because it puts the 3 exponent on the bottom so that when this cancels this out, we still get second squared on the bottom, right? And then this one, it multiplies it by amps, which is multiplying it by coulombs over seconds. And that's going to give us, well, coulombs on the top, which we don't want, and too many seconds on the bottom. So being able to be very like flexible with doing these unit conversions is going to be key. So like just get really, really like accustomed to like deconstructing them and reconstructing them and all of that stuff. That's probably going to be like the biggest thing aside from like understanding the physics and chem conceptually.
Yeah.
So I would say like importance, like conceptually understand is number one, and number two would be like being able to do dimensional analysis, unit conversions, and like three would then be like know the formulas. Uh,
Okay.
Obviously know like the formulas first because that's just the easiest thing to like get down first, but formulas without being able to understand it conceptually or without being able to, be able to be nimble with units, yeah, it won't work out. So,
Okay.
mhm.
Right. Sounds good. Thank you.
Yep. So,
Yeah.
oh yeah. So like I guess like just really quickly, I'll just touch upon this because you mentioned magnetic stuff. So magnetism starts to introduce the third dimension, which is why like the right hand rule.
Yes. Yeah.
Like the entire point of that is because when we draw stuff, it's in two dimensions. So the right hand rule means we can use our three-dimensional hand, right? So basically, if you have, so basically, let's see how I can do this quickly. A moving, so the magnetic force is, whoops, QV the sine theta. The sine theta just means that, and you'll see it in like torque and stuff, means that we're looking for the angle to be perpendicular or 90 degrees. But Q is a charge, V is a velocity, and capital B is a magnetic field. And you need these in order for something to experience a magnetic force. Meaning you need a charge, you need an external magnetic field, and you need the charge to be moving. Okay? So now let's say that we have, so X means we have a magnetic field that's going into the page. And let's say we have a charged particle moving with a velocity to the right. So in the right-hand rule, there's your thumb will be the movement of that charged particle. So for this one, it'll be like to the right. These fingers will be in the direction of the magnetic field. So the X's mean it's going into the page. So it's going to be like this, right? And the direction of your palm is going to be the magnetic force that it experiences. So its
Yes.
force is going to be up, right?
Yeah.
So like this is going to start to move like this. And when it's here, its velocity is there. Now tell me what direction the magnetic force is.
So you're saying like once it goes up.
So like it's yeah, it's going like this, and at this point, its velocity instead of it going to the right is now straight up.
So now it's gonna experience force going down.
So do the thing. Okay. So where's that force pointing?
To the left.
Yeah. And then this will go like this with the velocity here. Now, tell me.
Okay, yeah, now that's going down.
So then this goes here, the velocity here.
This is to the right again.
And there you go. So your moving charged particle, when it's in an external magnetic field, will experience a centripetal motion, centripetal force. And your centripetal force is mass times angular acceleration, which is just tangential velocity squared over radius. And we could equate that to the magnetic force, which is QVB. Sine theta, I already said that like the magnetic field is going in and the velocity is perpendicular, so the sine theta just turns into 1. And we can divide velocity and we can end up getting, or, well, we could divide velocity, and if we wanted to solve for velocity, it would be V is equal to QB over, oh wait, M divided by M. Wait, sorry. So mv squared over r is equal. Oh, so let's actually solve for r, the radius. Oops. So the radius, multiply it on both sides, is equal to mass times velocity divided by q times b. So this radius of the centripetal motion is proportional to the mass and velocity and inversely proportional to the charge and magnetic field. And so that could be a way that a mass spectrometer works, meaning if I had, something going here and it goes into a centripetal motion, the heavier it is, the larger this radius would be. So like something that's heavier can fall here, something that's lighter can fall there. But yep. So that's why for here, they're asking about like, okay, if we have a decrease in the radius, bless you, what can that mean happens here? So a decrease in the radius, we would want either a decrease in mass, decrease in velocity, or increase in charge or increase in magnetic field strength. So
Mhm.
an increase in magnetic field strength and a decrease in velocity. That works.
Gotcha.
All right, there you go. So awesome. Good, good, good. And yeah, get that Milesdown deck. Uh, do the essential equations, get all the equations down. Um, and we talked, did we say that we were going to take a test this time, or were we saying next time, or what?
I'm not quite sure. I mean, I feel like maybe I'll take a test. I guess I just need to make sure that I have all the content down. I mean, I have until Monday, so I plan on like studying tomorrow and Sunday, so I feel like maybe,
Okay,
but
okay, let's have you go over like, review this content diagnostic and get all that content down, make sure you have all the equations down. We can meet sometime next week to go over like some other questions that you might have content-wise. We can go over also like New World stuff.
Mhm.
And then you'll be prepared to maybe take a test like next week. Works out?
Yes. Yeah,
Awesome.
and fingers crossed I could take 3 tests before I take my test.
Yeah, let me see. Your test was June 28th, right?
Yeah.
Okay. So let's see. 1, 2, 3. You said AIM was 3 tests?
Yeah.
Yep.
Should I try to take more? I don't know.
No, no, no. That seems to work. Like,
Okay.
yeah. So, all right. Good stuff.
Great. Yes, thank you so much. I feel like the learning how to deconstruct the terms is definitely going to be super duper helpful for Chem Phys. So
Yep, yep.
definitely going to work on that this weekend.
Awesome.
Yeah.
So good luck, and I'll see you sometime next week. And yeah, it'll just be 170.
Gotcha. All right. Well, have a good weekend.
You too, okay? Take care.